Good day, everyone. This is Nicole S. Baliascas,
And this is Casey Marilympius, the
student of Grade 10 Hercules. Today, we'll be talking about one of the laws fundamental to chemistry. The law of conservation of mass, which sometimes is also called as a law of conservation of matter. The sake of consistency, we'll be interchanging these two terms, math and matters, for this video. Now, this topic is for grade 10 students for their fourth quarter.
Objectives: A. To understand that mass cannot be created or destroyed in a chemical reaction. B. To demonstrate the law of conservation of mass through laboratory experiments. C. To apply the principle of mass conservation to predict the outcomes of chemical reactions. Now, before we head into our lesson, let's take a look at the bigger. Our content standard for the student is to have an understanding of the chemical reaction associated and characteristics of properties, non-adding chemical reactions by taking a look at the law of conservation of mass, chemical reactions, and for our most essential learning competency, the chemical reaction associated with biological and industrial processes affecting life and the environment.
Now, let's go to review and connect. In order to relate the law of conservation of mass or matter to chemical reaction, we must first have an understanding of chemical. First, have an understanding of chemical reactions, especially this topic. So, chemical equation, types of chemical reactions. Reaction, especially these topics, to part of chemical equation.
So for the parts of the chemical equations, there are basically three parts, and the arrow or how we read this as yield of the chemical equation, the reactants products. But as an example, now the random molecules, now hydrogen gas as this molecule, no oxygen gas as our reactants before the arrow, so that the arrow on the other hand determines the direction of, so that reactants are usually found at the left side of the equation. Or as what you commonly read as yield, it tells us which side is the reactant. And product side, so reading the equation, we have two molecules of hydrogen gas and one molecule of oxygen gas. So our product for this example is two molecules of water as gas. The product or products is or are usually found at the right side of the equation. Now we also know in the development chemical equations such as this balance equation should show the same number of elements in both sides of the equation. Actually, we can find the balanced nature of chemical equation is rooted from the law of conservation of mass. By hitting balance equations, the different types of chemical reactions and their general forms are listed below, and combustion reactions. Now I am dwelling the specifics of these chemical reactions. So let's proceed. The law of conservation of mass, matter. Mass is neither created nor destroyed in chemical reactions. So what does the law of conservation of mass, or sometimes matter, actually say? It states that the mass in chemical reactions are neither created nor destroyed, or in other words, or in terms of matter is neither nor destroyed in chemical reactions. A mix of the hands is a chemical reaction, created nor destroyed in chemical reactions. So we have Antoine Lavoisier, our main contributor of the law of conservation of mass. So he is a French scientist. Carefully and repeatedly conducted different experiments on sealed glasses and jars while measuring their masses. So he conducted volume experiments in sealed containers such that he could still measure mass of the gases. For the different chemical reactions, that he conducted reactants before the reaction, and he observed that the mass of the reactants before the reaction were the same as the mass of the total mass of the products after the chemical reaction. Okay, in order to understand the law of conservation mass, let us first apply it to an actual and common chemical reaction. Alright, so can you tell me what object is depicted in the image in the screen? We will most likely have this end product. Okay, so yes, it is wood, specifically campfire. Okay, or we will observe this as an end product. We will have ash. Now initially, if I ask you to compare a great difference but the law of conservation, now initially if I ask you to compare the mass of the campfire wood. But the law of the conservation of mass state that in a chemical reaction, such as the burning of wood, mass can neither be created nor destroyed and initially. Okay, but in fact for this chemical reaction, we also have to consider matter. Look at the image. Well, from a pile of wood. Reaction, we also have to consider the other products, consider the gases. In chemical reaction, we also have to consider in this reaction, which is water and carbon dioxide, and added to the mass of the remaining amount of mass as the starting mass, weight, or mass rather into our example just to give amount of mass as the starting mass. Okay, so let's put to in order for us to visualize it more clear. So, and we got 1 kilogram as it mass. Okay, 0 kilogram. If we made a setup where we could have gathered and corrected all the gas is produced and weighed it according to the law of conservation of mass and total mass, 0.9 kilograms. So disclaimer, proportion in naturally, so this is just for us to visualize the unlock conservation of mass. So in proportion, not necessarily consistent other experiments. So because in every chemical reaction, matter can either be created nor destroyed, they can be transformed into different kind of matter, but essentially it would have the same components and their mass would be the same. So just to give us a clear picture on how it is transformed, let's have another example. Okay, combustions of methane. So now let's use the combustion of methane CH4 as another example for our discussion. So again, according to the law of conservation of mass or matter can neither be created nor destroyed. Using the example, mass make internet and how matter is transformed, redistributed or rearranged into new or different matter instead of being destroyed or created. Okay, so in the equation shown, we see methane is for reacting with oxygen to produce water and carbon dioxide. Based on the equation, we can see that both sides of the equation would have the same number of atoms of carbon, hydrogen, and oxygen. So basically, it is a balanced equation. The only difference is that they were put and called redistributed or rearranged into different compounds from methane and oxygen to water and carbon dioxide. We can simply see that there was no change in number of elements and both sides had the same amounts of atoms of elements involved, blood amount of the nitrogen of chlorine all throughout the reaction carbon, hydrogen, and oxygen. Lamba ama. Elements evolved so we can therefore visualize chemical reactions as the rearrangements of atoms and bonds, while the number of atoms involved in a reaction remains changed. So let us use this example to further understand the law of how does the law of conservation imply the mass of our reactants and products. Okay, so for potassium hydroxide readily reacts with carbon dioxide CO2 to produce potassium carbonate K2CO3 and water H2O. How many grams of potassium carbonate are produced if 224.4 grams of potassium hydroxide reacts with 88.0 grams of carbon dioxide? The reaction also produces 36 grams of water. Provided also below is a balanced chemical equation, but actually, in solving these kinds of problems, and we don't really necessarily need our balanced equation, but it is a good practice to write our balanced equations. But the tip here is that we have just always have to remember the law of conservation of mass, which is mass is neither created nor destroyed in a chemical reaction. So what we do is we simply list down the mass of our reactants in the mass of our products. So alam natin ding reactant sa tin ion carbon dioxide and potassium hydroxide. So we put in one side 88.0 grams and 224.4 grams and the Lanatan name. So we label it as X, our variable, and H2O, which has 36.0 grams water as our product or as one of the given products. So we put potassium carbonate and water, the mass of this, into one side of our equation. So mass of reactants is equal to mass of products. So 88.0 plus 224.5 grams is actually 312.4 grams. And in our equation is equal to X, the mass of potassium carbonate, plus the mass of water, 36.0 grams. Okay, and in order to find X, we subtract 36.0 grams in both sides away of the equation and we get 312.4 grams minus 36.0 grams is equal to X, or the mass of potassium carbonate, and if we answer that, we get 276.4 grams. Now, in order to check, we can substitute again X to our original equation. The value of X to our original equation, so 88.0 grams, just 224.4 grams, which are the mass of carbon dioxide and potassium hydroxide. As our reactants equal the mass of our products potassium carbonate 176.4 grams and water 36.4 grams. Now if you see that, check both sides of the equation, solve them that they are actually equal to 300.4 grams. So if we get the same amount for both sides of the equation, we know that we got the right answer. Alright, again, the law of conservation of mass, or matter states that mass in a chemical reaction is neither created nor destroyed. But before we head to our problem says, let's take a look if we're able to meet our most essential learning competency this video. So we were able to apply the principle of of conservation of mass to chemical reactions? Surely yes, as we have discussed earlier, following the law of conservation of mass, we create balanced chemical equations, and also by understanding that the law of conservation of mass and having a balanced chemical equation, we can identify the mass of specific components of our equation given data on the other components. That what we did, finding that's adding examples of potassium hydroxide and some effect. Alright, as for our content, the standard are supplementary material on the conservation of mass by Robert W. Stern. Okay, for our problem, set our first question or our first sample problem. Reads 8 grams of hydrogen reacts with some oxygen to make 72 grams of water. Figure out how much oxygen must have been used by applying the law of conservation of mass. So again, as I have stated earlier, these kinds of problems do not necessarily require us to use balanced chemical equations, and we can simply just remember this equation: mass reactants is equal to mass products, or to be more exact, total mass of reactants is equal to the total mass of its products. So we just write in one side of our equation the mass of our reactants at the sum of the mass of, and in the right side the mass of our products. So for this problem, we write 8 grams. The mass of hydrogen is given by the problem plus X, so the amount of, or the mass of oxygen needed equals 72 grams of water, or as provided by our problem, and we try to solve X. So by solving by rather subtracting 8 grams to both sides of the equation, we get 64 grams. And again, to check, we just simply substitute the value of our X to our original equation, which is 8 grams plus X is equal to 72 grams, and check if both sides of the equation show or give us equal values. So 8 gallons per 64 grams actually equal to 72 grams. So we know that 64 grams of oxygen must have been used to react with hydrogen to produce 672 grams of water. So that's all. Thank you for watching.